In a previous series of videos, we talked about infinite limits, and these were places where we had vertical asymptotes. For the function pictured, we would say that the limit as x approaches a from the positive side of f of x is equal to infinity. In this case, the answer is infinity. Or another way to put it is that the limit is infinity. I know, it means that the limit doesn't exist, but you get what I'm saying. Here we're talking about limits at infinity. And what we're going to see is that a limit at infinity is related to a horizontal asymptote. So let's say here for this function pictured, the limit as x approaches infinity of f of x is equal to some number L. Instead of the answer being infinity here, we're saying that x goes to infinity. Now we can formalize this limit statement, the limit as x approaches infinity of f of x is equal to L, by a definition. What the definition is going to say is that if x is big enough, then f is going to become really, really close to L, so as to become indistinguishable from L. Of course, math isn't about really, really close. Here's the definition. Let f be a function defined on some interval from a to infinity, then the limit as x approaches infinity of f of x equals L means that for every epsilon greater than 0, there's a corresponding number n such that if x is bigger than n, then the absolute value of f of x minus L is less than epsilon. Remember epsilon and delta before? Now we don't have an epsilon, now we don't have a delta, but we have an epsilon. Suppose this is my epsilon. What I'm saying is there exists some number n, in this case probably 0, such that if x is to the right of n, then the function and the limit have a difference that's smaller than epsilon. And then there's that whole for every epsilon greater than 0. So if I make this even smaller, then there exists some number n such that if I'm to the right of that n, then the difference between the function value and the limit value is less than epsilon. We aren't going to do anything with that definition. That's just the formal introduction of this concept of a limit at infinity. There's an analogous definition for a limit at negative infinity, and for that, the function would have to be defined on an interval from negative infinity to a, and then this would be like x is less than m for some number m, and everything else is the same. For this picture, that might mean that this graph ends up going to as it goes to the left, it's going to become horizontally asymptotic with this red line down here. And let's say that the upper limit here is L1, and then this lower limit here is L2. And you can see that a function can have two horizontal asymptotes, never more. It can have just one, but it can also have two. Like, why can it never have three? Picture another horizontal asymptote up here. If the function is going to approach there, I'm going to fail the vertical line test. Let's look at another definition of something that you already know about. The line y equals L is called a horizontal asymptote if of the curve y equals f of x if either the limit as x approaches infinity of f of x is equal to L, or the limit as x approaches negative infinity of f of x is equal to L. In this picture here, both the black dotted line and the red dotted line are horizontal asymptotes. Now, in the exercises for this section, we're going to make use of a theorem. If r is positive and rational, then the limit as x approaches infinity of 1 over r is equal to 0. Let me stop right now. So, for instance, the limit as x approaches infinity of 1 over x squared, here r is 2, is equal to 0. I'm not going to go through a formal proof of this, but I will appeal to the graph of the function. As x becomes infinitely large, 1 over x squared becomes infinitesimally close to 0. It also works for the limit as x approaches infinity of like 1 over the square root of x. That's also equal to 0. In this case, r is equal to 1/2. The proof of this would be based on limit laws, but I want to get into what the work is going to look like here. Here we're asked to find a limit or show it doesn't exist. Notice that it's the same function twice. In the first expression, we have the limit as x approaches infinity of 4x cubed plus 6x squared minus 2 over 2x cubed minus 4x plus 5. In the second one, it's the same function, but it's the limit as x approaches negative infinity. Notice if I attempt direct substitution, I will get infinity over infinity. That never tells me anything, so I need to do a bit of work. And when I'm finding a limited infinity, my work is usually going to be to divide in the numerator and denominator the largest power of x that appears in the denominator. In this case, since our denominator has a largest power of 3, right? 2x cubed is the term with the highest degree in the denominator. I'm multiplying numerator and denominator by 1 over x cubed. And we end up with the limit as x approaches infinity of 4, because the x cubed divides out of the first term, plus 6 over x, because 2 factors of x divide out for that term, minus 2 over x cubed. And in the denominator, again, for 2x cubed, all factors of x divide out, minus 4 over x squared, because 1 factor of x is going to divide out, plus 5 over x cubed. Now we have these terms, 6 over x, 2 over x cubed, 4 over x squared, 5 over x cubed. And according to the theorem we just talked about, all of those are going to go to 0. So our answer here is 4 over 2, which of course reduces to 2. In this case, we'll find that the limit as x approaches negative infinity is going to turn out to give the same result, which is 2. That's not always going to happen. And for more interesting situations, watch the next video.